Optimization problems. In this video, I will explain how to do them using a couple of examples. This is the first problem we're going to do, and it's a pretty common one. To start solving it, though, the first step is to draw a picture. Okay, so this is my drawing, but yours doesn't have to be this complicated. So how we set it up is that since we know it's a rectangular area of a backyard bordering on one side of the house, the fence will probably look something like this. And then because these two are the same length, we can assign those both to y, and we can assign the remaining side to x. And that can also let us develop this equation, which is this side plus this side equals 84, which is the amount of feet of fence we were given in the beginning. Okay, now that we have this equation, we need to come up with an equation for the area, which is this. Okay, so the next step is to put this equation in terms of one variable, which in this case, it'd obviously be easier to put it in terms of x. So you do that, and then you use this to substitute as x in the area equation, like so, and then you distribute the y between these two terms, getting you this, and then you take the derivative of this equation to get you this. The next step of this equation is to set this derivative equation equal to 0. And then from here, you just solve for y, like that. This point, as well as 0 and 84, are the candidate points for this equation, and they're where the graph of the area will either have its maxes or its mins. So next step is to make a sign chart to find the maxes, because we're looking for where it has the largest area, not where it has the smallest area. The first step in doing the sign chart is to find a value between 0 and 21 and plugging it into the derivative equation. I'm going to pick 10. So that'd be 84 minus 40, which would be 44, and that's positive, so we write a plus here. The next step is to do the same thing for 21 and 84. So I'm going to pick 40. So you substitute that in, that'd be 84 minus 160, which would be negative 76, which is negative. So you can tell by this that 21 is the maximum. Oh, and in case you're wondering what I did here, this is basically just showing that because between the interval between 0 and 21, since the derivative is positive, then the graph would be increasing, and since here it's negative, it'd be decreasing, and it helps us visualize where the maximum is. Now we can figure out the answer. So this, since it's the maximum, we know that it's the y value that will lead to the largest area, so that's the y dimension. Now we need to solve for the x dimension, which we can use this equation and substitute the y value we just found in to end up with this as our final answer. This is the second problem. It's pretty similar to the last one, but we're given the volume instead of the perimeter this time. Either way, the first step is still to draw a picture. This is my picture. It's simpler than last time, because there's really not that much to add this time, because all we have is the volume. Like last time, our next step is to write an equation for the problem. We use the formula for a volume of a cylinder and set it equal to what we know the volume is. After this, we also find the equation for the surface area of a cylinder. Now we put the first equation in terms of one variable. This time I chose to put it in terms of h. After this, we substitute this into the second equation, like this. We can also simplify this by canceling out the 2r here from the 2r here and multiplying the 500 times the 2. That leaves us with 1,000 over r there, which can be turned to 1,000 r to the negative 1th power, which will help us when we're taking the derivative. The next step is to take the derivative, like this. And after that, we set the derivative equal to 0, and then solve for r, which gets us to r equals the cube root of 250 over pi, or approximately 4.301. Now that we have this value, we can go ahead and form our sign chart. Again, we pick a number between these two and plug it into the derivative equation. This time, if you pick a number between these two, it's negative. Do the same here. If you pick a number between these two, it'd be positive. So make our lines to help us realize that that's the minimum. This being the minimum means it's the lowest value the radius can have and still lead to a volume of 500 centimeters cubed. So we have the radius dimension covered. Now, all we need to do is use this original equation here and plug the radius value from here into there, and we get the final height value. Well, that's about it. Hope this video helped you understand optimization better, even if it wasn't the most exciting. And thanks for watching.